Okay, so today's plenary talk is going to be on dissecting equations, as every Friday is, and we are going to talk about dissecting the equation of conservation of momentum. You guys are going over this week, and I have seen that the lab is going to involve impulse and definitely momentum conservation heavily, so I figured this would be a great equation to learn how to dissect. So if you remember from the previous videos, if you've watched them, we tend to just go through each piece and see what we can do here. So starting with this left-hand side of the equation, we have m1I. So what we're going to do is we're going to go through and we're going to identify every variable and what they mean. And so m1I is the initial mass of an object labeled as 1. So if you have so you have two different objects, and then you can say that this one is M1. Actually, you know what? I could do this here like this. This one is M1 because I'm recording on Zoom. It makes it a little delayed. So this is M1 and this is M2, and we're just going to go with this for now. And just for all intent and purposes, we'll call this M1I, call this M2I. And all we're doing is we're just labeling things. And so we're trying to stick with the theme of dissecting the equation. As you can see here, I've put these images in to help us try to, dissect the equation as we go. So we're going to say that there are these two objects just sitting out in space somewhere, and they've got some kind of velocity, and they're going to collide at some point in time. And so we need to go through and we need to continue to dissect by labeling what is V1I. What is the V1I? V1I is the initial velocity of the object labeled 1. Now, I want to point out here, because a question you might ask is, why did we label them 1 and 2? The answer to this is the labeling is arbitrary. This means that, we can choose the objects to be 1 and 2, an object 1 and 2. All right, so we continue and we say, okay, well, now what's M2I? We can probably guess now based on what we've been doing here that M2I is the initial mass of the object labeled 2. So then we continue and we say that V2I is the velocity of the initial velocity of the object labeled 2. Okay, so this defines and sets the stage for the rest of the dissection of this equation because we have just finished the left-hand side. All of this information pertains to right here. And you can kind of split this up by, we can say that green, oh, didn't want the whole thing. I only wanted this piece of it be highlighted, not the whole thing. Well, this piece right here is what we have accomplished. So what happens is now, in order to continue dissecting this equation to truly understand what's going on here, you have to understand that, I guess you ask yourself, what happens next? Well, what happens next is object one and object two are going to collide, are said to collide. Okay, so if they're going to collide, both of them have some kind of velocity. That initial velocity could be 0 for one of the objects, which is totally okay. Makes the problem easier if we're doing that. And once there is some sort of collision, maybe the masses change, maybe they stick together, maybe they bounce off each other perfectly. Depending on what happens, determines on what happens in the final or the right-hand side of the equation. Generally, we can write this like this because this is a very true statement. But where the complication comes in is what kind of collision occurs. So let's write that down. What kind of collision occurs? There's two different types of collisions. There are elastic collisions and inelastic collisions. So for conservation of momentum, this is very important. Very important that you understand that there are two different types of collisions, because in conservation of momentum, to determine what happens on the right-hand side of this equation, to truly dissect it, you have to say, okay, well, do we have an elastic or an inelastic collision? So if we consider an elastic collision, those are the collisions that bounce off each other. In other words, momentum is conserved. But not necessarily kinetic energy. Okay, so in an inelastic collision, the objects collide and stick together. Here, uh, kinetic energy is conserved. I believe I have not mixed that up. So if that's the case, then one of them is much simpler than the other, and the one that is much simpler is the one where they stick together. And if that's the case, the right-hand side shifts a little bit. So we have M1I, V1I plus M2, M2I, V2I equals M1 F V1F plus M2F. Oh. Okay. So in an inelastic collision, the right-hand side of the equation changes. M1 and M2 become some bigger mass M, and they have the same velocity. So V1F equals V2F. And so if that's the case, we can say that this is equal to V. And what we have here is I can factor that big V out of both sides. And remembering that we labeled M1 and M2, and we can be more specific here, we can say F, F, and we can plug this in and find that we have big M times big V. And so what do we have here? We have a big mass times a big velocity. So now we can redefine and continue dissecting our equation. So big M in an inelastic collision, big M is the combined mass of the two objects colliding, the two collided objects. Big V is the velocity of the combined object. So we see here that we have a mass and a velocity. So therefore, on the right-hand side, we have momentum. On the left-hand side, we have momentum, and it's just being added by the two different objects. And so therefore, momentum is still conserved. We have just redefined it in a way that accentuates inelastic collisions. I did say this backwards. So in inelastic collisions, momentum is conserved, not necessarily kinetic energy. And for an elastic collision, kinetic energy is conserved. So the reason why I had to go back through and redo that is because if we talk about elastic collisions, these are the collisions that bounce off each other. Therefore, their velocity is going to change. Since velocity is a vector, momentum might not necessarily be conserved. So if this is the case, then we need to, when we talk about elastic collisions, there are two parts to these equations. We have the conservation of momentum equation, and we also have the conservation of energy. Being that all of this energy is motion, we're just going to call it the conservation of kinetic energy, because kinetic energy is the energy of motion. And so if that's the case, you're going to need and you'll notice that there's a theme with these conservation equations. They all follow the same initial of the objects equals the final of the objects. But what happens in between isn't necessarily so easy. As you can see, we have now added a second equation to make sure that we can understand what's going on in the first equation. So if this happens and we have an elastic collision, we still have two separate bodies with their own kinetic energy and momentum. So what I will do is for the plenary talk that comes Monday, I will find a equation where we can use this dissection and we can go through conservation of momentum with conservation of kinetic energy. I hope that this benefits you. Have a great day.